Thank you very much, and thanks for inviting me to this very nice event. I should probably start with kind of an apologize, because some of the problem behind my talk is actually motivated by more classical physics and not so much by quantum physics, although the objects involved are just eigenfunctions of the Laplacian on certain sets. So of course they have an interpretation in quantum mechanics. So I'm going to speak about the hotspots conjecture that some of you may know. So the physical heuristics behind it is you look at a piece of, for instance, a piece of metal or something that is insulated, so no heat can get out or come in through the surface. You have an initial temperature distribution on it, and you wait for a very long time. Of course, the temperature distribution will converge to equilibrium. But what is happening on the way to that? We are particularly interested in the hottest and coldest spots in this medium. How do they move during this process? And somehow what one would expect that somehow if you look at the hottest and coldest spot, then they should move away from each other, because somehow the temperature at the hottest spot should cool down. Okay, I thought I made a mistake. One expected somehow the temperature at the hottest spot would cool down fastest towards the coldest one, so one would expect they would move away from each other. So they would potentially move towards the surface, somehow as far away from each other as they can. And if we try to write down what this means mathematically, then we would probably model this medium or this body by a domain in RD, say a bounded domain. We would consider the Neumann Laplacian on that domain, denoted by delta n here. And then we would consider the heat equation. The Neumann boundary condition just precisely incorporates the fact that the domain or the body is insulated, so no heat flux through the surface. And there is an initial heat distribution U0 imposed. So that's the form of the heat equation that we are considering here. And of course, we could formally solve this by looking at a semigroup generated by the Neumann Laplacian, and we could expand this. We could expand this into eigenvalues and eigenfunctions of the Neumann Laplacian. So we get this kind of expansion where psi1, psi2, psi3 are the eigenfunctions of the Neumann Laplacian, and mu1, mu2, and so on are the corresponding eigenvalues. We are assuming the domain that is a connected open set, so the first eigenvalue has multiplicity 1, and it is 0, corresponding to the constant eigenfunction psi1. So the whole first term in this expansion is just a constant, and then we get terms corresponding to the positive eigenvalues mu2, mu3, and so on. And the term that goes to 0 the slowest then is the term involving mu2. That is for a very large time. Somehow the dominating term concerning the shape of the solution is the one containing the eigenfunction psi2, corresponding to the first positive eigenvalue. And that means, so we are interested in somehow the maximum and minimum of the heat distribution for a large time. So we are basically interested in the maximum and minimum for large time. That will basically be the maximum and minimum of the eigenfunction psi2. That leads us to the hotspots conjecture in the form as it was mentioned in a lecture by Jeffrey Rauch in 1974 and was written down in the book of Cavol in 1985, namely, take psi2, let psi2 be any eigenfunction of the Neumann Laplacian associated with the eigenvalue mu2, the first positive one. Then psi2 achieves its maximum and minimum on the boundary or even only on the boundary. Of course, you could easily test this conjecture for those domains, for those shapes for which you can compute the eigenvalues and the eigenfunctions explicitly. For instance, for the interval, obviously, it's just a cosine going from its one maximum to one minimum. So, of course, it takes its maximum one endpoint and the minimum on the other one. You could compute that for rectangles, cubes, balls, and so on, for a few explicitly computable triangles. And you will always see that this conjecture is satisfied for these domains. Then there are by now quite a few results, positive results for two-dimensional domains, but basically nothing for higher dimensions, nothing non-trivial. So among the first results was the proof for obtuse triangles or 2D domains that have certain symmetries. Then there is a class of domains called Lip domains. That's a class of two-dimensional domains with the property that they are bounded above and below by Lipschitz continuous functions whose Lipschitz constant is at most 1. So it is bounded above and below by functions whose slope is between 1 and -1, as in this picture. And for this class of domains, the hotspots conjecture was shown by Attar and Birdsey. And the most recent, the most recent breakthrough result, so to say, is a proof for all triangles, and even that is highly non-trivial, by Judge and Mondal in 2020. Then it is known that the hotspots conjecture is not always true. It fails for some certain domains with holes. So one can, not for all domains with holes, but one can construct certain examples. And what you see in this picture is one example of a domain and a numerical computation on that, where the hottest and coldest spots are not on the boundary, but somewhere inside. And actually the construction by Birdsey is a pretty similar domain, similar to this picture where he proved explicitly that the maximum and minimum are inside the domain. But it is interesting that there's very recent numerical work shedding some light on this kind of examples. So one might still hope to prove the hotspots conjecture in this form, namely assume that omega is simply connected, then for any eigenfunction psi2 corresponding to the lowest positive eigenvalue, it may achieve its maximum and minimum only on the boundary. I should mention there are some related results to the conjecture, like more quantitative results, by, amongst others Steinerberger. Very recently, there's what I mentioned, the numerics done by Kleefeld. And there are related results for operators on discrete and metric graphs by a couple of authors. The proofs of the positive results that I mentioned here can basically be divided into two classes. One class is using a probabilistic interpretation. That is basically all domains or all results that involve Birdsey as an author. The other class is following or tracing critical points of eigenfunctions under perturbations of the domain. So you start with a domain for which you maybe know where the critical points are, or that there are no critical points or something, and then you trace how they change when you change the domain. I was for a long time wondering, shouldn't one be able to use variational methods instead to prove something here? So obviously the hotspots conjecture is true for a domain if it is possible to exclude critical points of the eigenfunction corresponding to mu2. So we would like, if we can exclude critical points, which is of course much stronger than the actual hotspots conjecture, then we can prove it. And somehow my idea was one could actually study partial derivatives of eigenfunctions that still would solve the same differential equation, minus Laplacian of the partial derivative is equal to mu2 times this partial derivative. Just obviously they satisfy other boundary conditions. And if one could show that these would be eigenfunctions of a Laplacian with appropriate boundary conditions corresponding to the lowest eigenvalue of that for these boundary conditions, then one would probably be able to show something that these functions would not have a sign change by somehow the classical Courant type argument. So the hope would be to find some direction in which the partial derivative of psi2 would be strictly positive by Courant type nodal arguments. So let me just recall very briefly. So the typical argument for that would be if you, for instance, have an eigenfunction of the Dirichlet Laplacian corresponding to the lowest eigenvalue, then it is a minimizer of the classical Rayleigh quotient, where you minimize over all functions in H10 that are not constantly zero. And then you take just the modulus of the eigenfunction of this minimizer, and taking the modulus does not change the Rayleigh quotient. That means that, and taking the modulus does of course not change that the function is in H10. So also the modulus of phi is a minimizer, and therefore also the modulus of phi is an eigenfunction corresponding to lambda 1. In this case for the Dirichlet Laplacian. And then one uses somehow the maximum principle for subharmonic functions to show that actually this function cannot be zero at a point inside the domain, since it is non-negative. And somehow the idea was, couldn't one use this kind of arguments for the partial derivatives of psi2? But of course the problem is, it's not very clear which boundary conditions the partial derivatives would satisfy. And then I got basically stuck for a couple of years at this point until I noticed it is much more natural actually not to consider the partial derivatives separately, but just consider the whole gradient. And that led me to the following kind of auxiliary self-adjoint operator, which is the Laplacian acting on vector fields with appropriate boundary conditions. So actually, if we look at this operator, the boundary conditions are that there's some regularity, of course, in terms of Sobolev regularity that I did not mention here on the slide, but the boundary conditions are, we consider only vector fields that are orthogonal to the normal on the boundary, so they are tangential basically on the boundary. And they satisfy this kind of non-rotation condition, but only on the boundary. So that are the boundary conditions that we impose. And they turn out to be the right ones, because now if I take actually any eigenfunction of the Neumann Laplacian, except for the constant eigenfunction, and I look at the gradient, then the gradient of that will be an eigenfunction of this operator, because it will obviously component-wise still satisfy the equation minus Laplacian of the function is equal to mu2 times the function, and it will also satisfy these boundary conditions. So the first one is, if you plug in the gradient of psi2, is just the Neumann boundary condition. And the second one comes just from the fact that it is the gradient of a function, so that it has a potential. It would even be satisfied on the whole domain. What is very interesting about this operator, it is not only gradients of Neumann Laplacian eigenfunctions that are eigenfunctions of this operator, but if I take any eigenfunction of the Dirichlet Laplacian and I take their like perpendicular gradients, so I take this vector field that is pointwise orthogonal to the gradient. Probably there's a better name for that. Then these would also be eigenfunctions of this operator and would also, in particular, satisfy these boundary conditions. For instance, so if I take a function that satisfies the Dirichlet boundary condition, then it is obviously constant along the boundary. So the tangential derivative along the boundary is equal to 0. And that is actually the same thing as this thing being orthogonal to the normal vector. So we have constructed an operator whose eigenvalues are actually all eigenvalues of the Neumann Laplacian and all eigenvalues of the Dirichlet Laplacian, and maybe or maybe not something more. Actually, what one can show, if I take an orthonormal basis of eigenfunctions, of non-constant eigenfunctions of the Neumann Laplacian, and I normalize them appropriately, then I get actually an orthonormal basis of a subspace of the vector valued L2, namely of the space of gradients of H1 functions. If I take these perpendicular gradients of all Dirichlet Laplacian eigenfunctions and I normalize them appropriately, then I get an orthonormal basis of another subspace of the vector valued L2 space, namely the perpendicular gradients of H10 functions. And then there's something that is pretty well known among people who work with vector valued operators, like, for instance, Stokes or other things, and that is the so-called Helmholtz decomposition. And actually, in the case that the domain omega is simply connected, the Helmholtz decomposition is as simple as this equation, namely the vector valued L2 space can be decomposed into the space of gradients of H1 functions and the space of these perpendicular gradients of H10 functions, meaning that we have actually constructed an orthonormal basis of this space consisting of eigenfunctions of the self-adjoint operator, and we have constructed an orthonormal basis of the second space consisting of eigenfunctions of this operator. That means there cannot be any more eigenvalues and eigenfunctions of this operator in the case that omega is simply connected. Otherwise, there is something more. So the consequence is that the spectrum of this auxiliary operator consists of all non-zero eigenvalues of the Neumann Laplacian and all eigenvalues of the Dirichlet Laplacian, including multiplicities. And interestingly enough, somehow useful is the fact that actually the lowest eigenvalue of this operator then must be the lowest positive eigenvalue of the Neumann Laplacian, because according to a classical result by Polya, the smallest positive eigenvalue of the Neumann Laplacian is always strictly below the first eigenvalue of the Dirichlet Laplacian, telling us that the first eigenvalue of this operator is actually exactly the first non-trivial eigenvalue of the Neumann Laplacian, and the corresponding eigenfunctions are exactly gradients of Neumann Laplacian eigenfunctions for this operator. That means we could get another variational principle for the eigenvalue mu2 of the Neumann Laplacian if we just compute the quadratic form for this operator. And one can do that and we'll get the following thing. So let omega be a bounded simply connected domain, and then there are some regularity assumptions for the boundary, piecewise smooth, and if there are corners, they should be convex. Then the first positive eigenvalue mu2 of the Neumann Laplacian is given by this minimization problem, namely that looks like the usual Rayleigh quotient just for vector fields, but there's an extra term here that involves the curvature of the boundary. And yeah, you get the first eigenvalue by minimizing this Rayleigh quotient over the form domain, and the form domain will contain the condition that only vector fields are admitted that are orthogonal to the normal vector on the boundary. And then you have equality, of course, if and only if U is the gradient of a Neumann Laplacian eigenfunction corresponding to mu2. And let me maybe, that seems, to the best of my knowledge, be the first variational principle for mu2 that involves gradients of eigenfunctions instead of the eigenfunctions themselves. And it seems that the fact that omega, or the assumption that omega is simply connected, appears very naturally in this approach through the particular form of the Helmholtz decomposition. If the omega is not simply connected, then you get, like, you can decompose this auxiliary operator A into actually 3 parts, and one part then corresponds to certain harmonic functions, so you get an extra eigenvalue 0. So can we now use this variational principle to say something about the hotspots conjecture? So could we conclude that the components of the gradient of psi2 do not change sign? So we try the same approach as in the classical Courant argument. So we take a minimizer, which is the gradient of some eigenfunction. We take component-wise the modulus, and we wonder, is this a minimizer as well? And if I take component-wise the modulus, then the whole Rayleigh quotient will not change. That is fine. But will this vector field still belong to the appropriate test space? That is the question. And if you look at this picture, this is just an example domain, then you see there are different situations. So if the domain is rotated like this, and you look at this green side, then the normal vector would look like this. So it has one positive and one negative component. The u1, u2 are the components of the normal vector. They have, one is positive, the other one is negative. So for the vector field u, in order to satisfy this condition, both components of u have to have the same sign. And now if I take the modulus of both simultaneously, then obviously this is still satisfied. So this just means possibly having a minus sign in front of this equation. So that is fine. If I look at this situation here, the normal vector has 2 positive components. That means that u1 and u2 have to have opposite sign. And now if I take the modulus of both, this property is destroyed, and you will no longer have vector fields that are tangential on the boundary. So if you have such sides after rotation, somehow, if after rotation you have such sides, that is bad. But if after rotation you can reach a situation where you only have sides of this type, you are fine. So the argument works actually if the normal vector, if almost all normal vectors, or the normal vectors at almost all points, point into the closed second or closed fourth quadrant. That's the case, for instance, for the domain here in the picture. And then actually you can think about what kind of domains these are. And actually it will turn out that if you rotate this by like 45 degrees in negative direction, then you get actually a domain that is has the graphs of 2 Lipschitz continuous functions with slope at most 1, or between -1 and 1. So you actually arrive exactly at the class of Lip domains that was studied by Attar and Birdsey. So what you get in this way is kind of a reproof of Attar and Birdsey's result. So if you have a Lip domain and you rotate it in such a way that the normals point into these directions, then you can actually show with this Courant type argument that mu2 is simple, except in the case that omega is a square, which would be allowed. And both partial derivatives are positive everywhere in omega, except in the case of a rectangle where one of them is constantly 0. So in particular, the hotspots conjecture is true for Lip domains. So this is not a new result. It is the first, I think it's the first purely analytic proof of this. And it is once you have established the variational principle, you can prove this in like half a page, basically. There are some, so far somehow this is a reproof, but, and here are just a few pictures of what you get. That these are just three-lip domains, and through the monotonicity or the positivity of the partial derivatives, and thus the monotonicity of the eigenfunction, in certain directions you will then see that there are unique coldest and hottest spots in all these examples. And let me basically conclude with just showing a few perspectives and giving some final remarks. So all this was for 2D simply connected domains. And of course, some of the variational principle does not require anything on the directions of the normal vectors. So it does not require that the domain is a lip domain. One could still hope to show something for more general classes of domains. Of course, it's not, one cannot expect anymore that both partial derivatives are positive inside the domain or do not have sign changes. This will not happen anymore, but there could still be certain directions in which the eigenfunction is monotonous. And this is something to be explored in the future. Then one could think about domains with holes. In this case, the auxiliary operator would have a third part whose domain consists of certain harmonic functions. And one can actually argue that the number of holes of the domain is equal to the dimension of this eigenspace 0 for the auxiliary operator. And then, so that might give somehow a tool to study more properly what happens actually for non-simply connected domains. And finally, it is interesting, of course, to do something similar for higher dimensions, since there are basically no non-trivial results on the hotspots conjecture in 3 and higher dimensions. It should be possible to derive a similar variational principle in higher dimensions, though there are certain kind of phenomena appearing that are different from the 2-dimensional case. And we have started studying this together with James Kennedy. But I think actually the proof for at least a certain class of non-trivial 3-dimensional domains is somehow in reach here. And that's probably a good point and a good point of time to stop my talk. Thank you for your attention.